Hello everyone, welcome to the lecture series on Foundations of Deep Learning Concepts and Applications. In the previous session, you have learned how convolution works for RGB images, which has 3 channels, and you have also explored the other 3 layers of CNN, other 3 components of CNN. You have seen how ReLU layer activation function works, and it is mainly used for introducing the nonlinearity, where all the negative values will be converted to 0. And then we have seen the pooling layer, and here in the pooling we have 3 different types. We have max, average and minimum pooling, and this is mainly used to reduce the spatial dimension while retaining the key features. And the last we have seen the flatten layer. And why do we require a flatten layer? Flatten layer is mainly, it acts as a bridge between convolutional layers, which is mainly responsible for extracting the features, and then the fully connected, which is mainly responsible for the classification part. So, between the convolutional blocks and then the dense layers, we have a flatten layer which acts as a bridge. So, in this particular today's session, we will look into a regularization technique, that is a batch normalization. We will look this in detail. So, batch normalization, what exactly it is? It is a regularization technique which is mainly used to reduce the overfitting problem. And batch normalization is one additional layer in a neural network. And when we say it is one additional layer, now where do we place this batch normalization? The batch normalization can be placed either before the activation function, or it can be placed after the activation function. So, there is no particular rule that it has to be used before or it has to be used after. It can be used anywhere before activation or after activation. So, whatever the code that you are seeing here, this code is an implementation on a multi-layer perceptron, where we are not using any batch normalization. So, we have an input being passed to the first hidden layer, which has 128 neurons, and the activation function used is ReLU, and this is the second hidden layer, and this is the third output layer. And if you want to use a batch normalization, this is how you will be using a batch normalization. First we are passing the input, then number of neurons, then batch normalization, then we are adding the ReLU layer. Then we have this is all this is equivalent to the first one, but here it is without using, and here it is with using a batch normalization. And the second here we have not used, and then here we are using, and this is how we write the batch normalization. So, this is the implementation where the batch normalization is applied before the ReLU activation function. So, let us now understand what is the need for batch normalization, why do, and what is the working mechanism. Whatever we are seeing, this is an neural network that we have built, and whenever we train a neural network, so we require a data set. This is the data set that we have. Whenever we train a neural network, we do not pass the entire data set at once. Then how is that we pass? We pass them as an sub batches, or we pass them as mini batches. We pass a small subset. First we will be passing these 5 samples, then we will be passing these 5 samples, then we will be passing these samples. Now, if you look into each of this batch, each batch has its own samples, all these are the samples, and if you look into, some sample values are very small and some sample values are very large. If you see, if you look into these values of one batch, if you look into these values of this batch, and if you look into these values of the third batch, some values are small, some values are very large, and some values are in between. Now, what exactly as a result? As a result of this, the mean and standard deviation may differ across the batches. There is a mean for the mini batch 1, there is a mean and a standard deviation for the batch 2, there is a mean and a standard deviation for the batch 3. If you look into the mean, if you see for the first batch, if you consider the height, mean of the height is so much, and the standard deviation of the height is this. Similar way, the mean of a second batch and the standard deviation of a second batch. Similar way, the mean of a third batch and the standard deviation. So, there is a difference, there is a change in this, the mean and the standard deviation is differing across the batches. Now, what exactly is the problem? As a result, the output of layers, the you know, when you are passing this particular data, whatever the output comes from the layers will have different distribution across the batches. When I say distribution, the distribution here is mean and standard deviation. Okay. Now, the mean and the standard deviation values going into the layers are different each time. Do you agree to this? This is what is the problem here. Now, if this is the case, what exactly happens during a training? When a training starts, now what exactly the model will do? You are passing the first mini batch. Let me erase this. You are passing the first mini batch to a neural network. Now, we know that during a back propagation, the model learns the weights and bias, and the model learns the weights based on this current pattern. Now, what if this is the data that you have passed, if this is the mini batch that you have passed, then the model will learn the weights and bias based on the current pattern of this data. Now, model adjusts its parameters. What parameters? The weights and bias. The model adjusts its parameters to fit to this particular mean and standard deviation, correct? Now, once the model has adjusted its weight and bias for this particular mean and standard deviation, now you are passing the second mini batch. Now, for the second mini batch, you are seeing that the values are completely different. Why we are saying that the values are different? Its mean and the standard deviation values are now different. Then, whatever the previous adjustments that the model has made will no longer fit to this new pattern for this new data, will no longer fit. Then what the model has to do? The model has to, or the network has to readjust again. Okay, the network has readjusted. Then you are passing the third mini batch. When you are passing the third mini batch, again there is a different mean and then standard deviation. Then whatever it has learnt again, all of this has to be readjusted. So, this is the problem. Now, how do we solve this particular problem? This problem is occurring because the input whatever is being passed to each layer is having a different mean and then the standard deviation. So, and for each batch it is changing. This is the problem. So, what is one solution to this? Can we normalize the values? How do we normalize the values? So that the mean and the standard deviation will be 0 and 1. So, this is what is one solution to this. Whenever you are passing the input, normalize the values and then pass. So that irrespective of whatever may be the values here, we are making it as unit Gaussian, where the mean will be 0 and then the standard deviation will be 1. Okay. Now, input is passed only here? No, right? Input is coming even to the first hidden layer, input is coming to the second hidden layer, input is coming to third hidden layer also. So, why to do normalization only at this input? Can we do normalization at every of the layer where input is being passed? This is a good approach, right? if this is good for stability. So that any input which is passed, irrespective of whatever batch that you are passing, whatever the samples that we are passing, its input will have the same distribution, mean will be 0, standard deviation is 1. Okay. Rather than just passing only at the input, we are now passing at every layer. Then how do we achieve this? We achieve this using a batch normalization. Okay. Now, there is one important step here. So, what is that we have done? We are calculating the mean, we are calculating the standard deviation, and then we are normalizing each of the values. So, how are we normalizing? We are taking a value, subtracting it with mean divided by the standard deviation. We are normalizing each of the values, so that when we take the mean, so if you take, it is 160 minus the mean divided by the standard deviation plus some constant value. Then you will take 162 minus mean divided by so you will normalize each of these values that are here. Similar way, you will normalize all of the values, so that the always, irrespective of any batches, any kind of a value, its mean, the input that is passed will have a same distribution. Rather than focusing only at an input, we are normalizing at every of the input. So, we are achieving it using batch normalization. Now, there is one restriction that we have put. What is that restriction? It is good for stability that every of the input values you are normalizing, but it is too restrictive. Now, we are limiting the model's freedom to learn the best internal representation. How are we restricting? Any input which is going as a unit Gaussian, which is having mean 0, standard deviation 1. So, is it not some sort of a restriction you have put to the model, that any input which is coming is already a restricted input. So, that is resolved by batch normalization by using this particular step, which is a scale and shift. There are two parameters called gamma and beta. These are learnable parameters. These will adjust the scaled values, normalized values with the help of two learnable parameters. Then you are passing it to an activation function. Finally, the scaled and shifted value is passed to an activation function. So, this is what is batch normalization. So, in short, we are rather than directly passing the values to an hidden at a hidden layer or at an input layer, we are normalizing the values, and then we are passing the values, passing the input. Now, let us take this one example and let us understand how batch normalization works. What are each of these steps? Let us understand this with an example. So, here if you see, this is the steps of batch normalization. So, batch normalization, the word itself says it works for a batch data samples in batches. So, let us assume this is one batch where we have 5 samples, we have 3 features, height, weight and age. Now, we want to build a neural network, and then let us understand what exactly is the operation that is taking place. Now, I am passing the first sample S1. S1, if you take this as S1, S1 is having totally 3 features, height, weight and age, and this is the hidden layer. And in the hidden layer, how many neurons are there? There are 5 neurons. So, when you establish this connection, the very first operation that we do here is it not we perform this operation? Height multiplied with the weight, then the second feature weight will get multiplied with its weight, and the age will get multiplied with this weight, and there is a bias term. Okay. So, this is the first operation that takes place. Now, so now is it not at Z1 we are calculating this at this particular node, what is that we are calculating? We are calculating height multiplied with the weight, and the feature weight gets multiplied with that weight, age gets multiplied with the weight plus bias. So, that is what for S1 to this neuron. Then is it not you establish this connection, and then here at Z2 you will once again calculate height multiplied with the weight feature multiplied, age gets multiplied plus bias. Then at the third you will calculate, here also you will perform the operation, here you will perform the operation, here also you will perform the operation. So, if this is the hidden layer, what exactly we are doing? We are passing the first sample, and for the first sample at this particular node, can we write it as for the first sample first node? So, is it not we have calculated this for so look at this. So, this is Z11, this is the first sample second node, this is the first sample third node, first sample fourth node, first sample fifth node. So, this is what we have calculated for the first sample. Now, what you will do, since it is an mini batch or batch normalization, now you will pass the second sample S2. When second sample is passed, what is that you will calculate? Second sample first node, once again it will be height multiplied with the weight, then it is weight multiplied with the weight, then age multiplied with the weight and bias. So, similar way here you will calculate second sample second node, second sample third node, second sample fourth node, second sample fifth node. So, is it not we get this for the second sample for all of these 5 nodes? Similar way, when you pass S3, is it not we get these? When we pass fourth sample, is it not these values? When we pass fifth sample, it is these values that we get. So, I will pause here for a few seconds. I want you to understand what exactly we have done. So, we have passed the samples and we have calculated the values for each of these nodes at a hidden layer. Okay. Now, once we complete with this, have we not completed one mini batch? One full batch of data we have passed. Now, by end of the first batch, is it not at this node we have all of these values? Is it you know, now I think you will be able to understand how did we get these values. When we passed first sample first node, when we passed second sample, this is the second sample first node, when we passed third sample first node, when we passed fourth sample first node, when we passed fifth sample first node, right. Now, what is batch normalization says? First calculate the mean. How is that you are calculating the mean? You will add up all of these values and then you will divide it with 5. You will be adding the mean, you will be calculating the mean, you will calculate the variance, and square of it is a standard deviation. So, what did we get? We have calculated the mean and the standard deviation for the first node. We have calculated it for the first node of hidden layer. Similar way, at a second node, we are still with the batch only, first batch. For the first batch, when we passed S1, we got first sample second node. Then when we passed second sample second node, when we passed third sample third sample, second node, fourth sample, when we pass to fourth sample, second node, fifth sample, second node. So, then you will once again calculate the mean and then the variance, standard deviation here. Similar way, at Z3, at this node, we have these many values, you will calculate its mean and standard deviation. For this particular node, we have these many values, you will calculate its mean and standard. For this particular node, we have calculated this. Okay. So, towards the end of now what we have done, we have completed the first mini batch, and let us assume you just have one hidden layer and you have your output layer. We have only hidden layer and we have this output layer. Now, what we have done so far, we have calculated summation, and we have calculated the mean and standard deviation. So, towards the end, for every of the node, we have calculated mean and standard deviation. I hope up till this it is clear. Now, once we have completed the first batch, once we have calculated the mean and the standard deviation for each of the node at a hidden layer, we have still not passed to an activation function. So, next step is every of these values should be normalized. We have to normalize this. So, from here on, let us take an example and then understand. I hope up till this it is clear. Now, let us assume whatever the values that we have here, let us assume those values, there are 5 values here, right. Let those 5 values be this, 2, 4, 6, 8, 10, just for an understanding purpose, understanding the remaining steps, we have taken these values. First step, you will calculate the mean and then the standard deviation. So, how for all of these values we have calculated mean and standard deviation. Now, we are calculating the mean and then standard deviation. How did we calculate it? 2, 4, 6, 8, 10 divided by 5, and then the standard deviation you are calculating. Now, we got this mean and this standard deviation. Now, we have to normalize all of those values. Which values? You will be now normalizing all of these values. How will you normalize? This is the formula to normalize. So, go back and then see how we are normalizing it. So, Z value is 2. So, if you substitute the values Z I dash is, Z value is 2 minus the mean of it is 6 and the standard deviation is 2.828, and we are adding a small epsilon value just to ensure that the denominator will never be 0. So, 0 point very small value 10 to the power of minus 5. It is this, a very small negligent value is being added. So, whatever is the resultant that you will get here, that is what is the normalized value of that 2. Similar way, you take the second value, you will normalize it. How will you normalize? In this place, you will write now 4. Now, in the next, you are going to change this value. We are going to change this value and you get this. Then you will change here 8, you will get this value, and here you will make it as a 10 and you get this value. So, what did we do so far? We have calculated. Let me go back and then show you. So far, what did we do? We have completed this step. We have obtained 5 different values because 5 samples are being passed, 5 different values we got, and then we have calculated its mean and the standard deviation, and then we have normalized all of these values. Why we are normalizing? Because we are just ensuring that the input that is passed to the next layer should have an should be an unit Gaussian, 0 mean, standard deviation 1. So, this is our intention. So, we have normalized the values. Now, so far we have completed this step. Now, what exactly is this? Now, let us understand that part. Now, so what is here? We are too much restricting the model. Why we are restricting? Although it is good that you are ensuring that any input that is passed is coming from a same distribution or having a uniform. But instead, this is actually introducing a kind of a restriction to the model, because this limitation that always the making input normalized one, maybe we are taking away model's freedom. So, to introduce that model of freedom, there are two parameters, gamma and beta. Now, since it is the first mini batch that we are doing, for the first mini batch, the gamma and beta value will be 1 and 0. So, that is initialization. Gamma value will be 1 and beta value will be 0. So, what is when beta value is 0, this whole term is not there, and when gamma is 1, anything you multiply 1 with some value will be that value only. Therefore, you see, for the first mini batch, you are passing values as it is. Why we are passing values as it is? Because gamma value is 1, beta value is 0. Now, so far what we were doing, whenever we pass an input height, then weight, age, when this is passed to an neuron, first you will be doing a summation, which is z equal to height into weight, weight into weight plus age into weight plus bias. This value, whatever is the z value was passed to an activation function. But now z value directly we are not passing to an activation function. We have normalized that z value and then we have scaled and shifted, then whatever is the y value that we have obtained, now that is passed to an activation function, max of 0 comma whatever is this y. This is passed to an activation function. So far this directly we were passing, now it is not this, it is these values are passed to an activation function. This is how the batch normalization is. Before we are passing the value to the next layer, we are normalizing the values and then passing. Because we are normalizing, we are restricting the model. In order to remove that restriction, we are introducing two other parameters, gamma and beta. Now, what will happen for the second mini batch? Now, once you pass it to a neural network, the first mini batch, you are going to get the loss, then you are back propagating. When you back propagate to update the weights and bias, you will now also update this gamma and beta. How will you update this? What is the weight updation formula? W nu is equal to W old minus learning rate derivative of loss with respect to the weight. The same is applied even here also. Look at the way that we are updating gamma and beta. It is gamma nu is gamma old minus learning rate derivative of loss with respect to gamma. Similar way for beta. For the second mini batch, you will once again go through all the steps, but this time gamma will not be 1 and beta will not be 0. You are going to update this. When you update, maybe the gamma value will be either 1.02 or it will be 0.98. I am just giving an example. So, for the next mini batch, when the samples are passed, you will get this z value. From z you are going to get this normalized z value. This normalized values are passed to this gamma 0.98 multiplied with some value plus beta, it will not be 0, you will have some value. Let us assume it is 0.4 into some value. So, here you are giving the this particular step is actually giving the freedom to the model to scale and shift the normalized values. Why to have always the normalized values only? Can we have some freedom? That freedom is actually introduced by using gamma and beta. So, that is the working mechanism. See, towards the end it is actually these values which are passed to an activation function max of 0 comma x. This x is these values. Earlier the z was directly passed to an activation function. Now z is not directly passed, z is going to normalized and then going for this scaled. The scaled and shifted values are passed to an activation function. Now, so this is all what we have done up till this particular. You have calculated mean, standard deviation, normalized, step 3 is done, then you have passed to step 4 activation. So, now whatever is the output, that is then passed to an output layer, that is passed to an output layer. So, this is how. Earlier it was a z value passed to an activation, now directly it is not passed, it is going through all of these steps and then you are passing through. Now, at the end of one mini batch, how you are calculating mean and standard deviation and how you are learning this gamma and beta. There are 2 other parameters also we should calculate and just keep it. We are not using, we are not learning those, we are just calculating and we are storing it. Now, what are those 2 parameters, or those 2 are, you should also calculate something called moving mean and moving variance. Now, for the first mini batch, for some time let us not bother about this part, just look only this. For the first mini batch, you had 5 samples and then there were 5 neurons at a hidden layer. For each of the neuron, you have calculated mean and variance, standard deviation. So, for second you have calculated this, for third like this, for every of the first mini batch you have calculated these values. Along with that, now you should also calculate moving mean and moving variance. What is the formula to calculate moving mean and moving variance? This is the formula. So, 1 minus momentum is one constant term that you will be adding, and that constant term usually will be value closer to 1, okay, and this mu value will be this mu 1, okay, into mu 1, plus you have a momentum term alpha, then there is a initial, for the first mini batch we have a moving mean. Now, we have still not started anything, it is the first mini batch that we are getting. For the first mini batch, we do not know what is this moving mean and moving variance value, we do not know these 2 initial values. So, the initial values we take moving mean as 0 and the variance we take it as 1. So, when we take moving mean as 0, anything you multiply with 0 will be a 0 term only, this whole term does not exist. Therefore, you see this formula, this equation, 1 minus momentum is this part and this mean is actually this mu 1. So, this is what is moving mean we have calculated. Let us see what is the role, why are we doing this, let us understand. Then how is that we are calculating moving variance? It is 1 minus momentum, then this variance is this standard deviation plus momentum into this whole term is 1. Therefore, we are getting this equation. I hope this is clear to you. It is still not explained why, it is only explained to you how to get this moving mean and moving variance. For the first mini batch, the moving mean value will be 0 and moving variance value is 1. So, this is how you are now calculating for Z1, Z2, Z3, Z4, Z5. What are we doing? For every of the neuron in the hidden layer, we are calculating these. So, which means for the first mini batch 1, we are calculating since there are 5 neurons at a hidden layer, and for every of the neuron, how we have calculated mean and standard deviation, like we are also calculating moving mean and moving variance, we are also calculating. So, which means for first mini batch, for 5 neurons at a hidden layer, how we have 5 mu and variance or standard deviation, we have 5 moving mean and moving variance. And for the first mini batch, the value of this will be 0 and this value will be 1. Now, you with this the first batch is completed. You are now getting a second batch data. When you are getting a second batch data, for second also you have 5 neurons. So, for every neuron you are calculating its mu and variance. For every of the neuron at a hidden layer, you are calculating mu and standard deviation. I am sorry if I am using variance again and again, square root of it becomes a standard deviation. Okay, so it is a mu and a standard deviation that we are calculating. Now, for the second mini batch also we should calculate moving mean and moving variance. So, you go back and then substitute the values. So, it is 1 minus momentum, and this mu will be this value mu 1 plus we have momentum alpha. Now, what is moving mean for the second mini batch? For the second mini batch, moving mean becomes, you have to use the first mini batch associated moving mean. What do you mean by this? You are calculating for the Z1. For the Z1 second batch, use first batch moving mean. Whatever is the result that you have obtained, that is stored in one variable, that variable will be the moving mean. For the variance, moving variance, this portion earlier it was 1, but now you are doing for the second mini batch. For the second mini batch, you will be using this. Can you able to see? We are using the first mini batch associated values. What do you mean by associated? You are calculating for Z1. Z1 of mini batch moving mean and moving variance we are using. Moving mean and moving variance here we are using it. Similar way, can you see for the second neuron, it is a Z2, you have got mu 1 and mu 2 and mean and standard deviation. Now, here you have to calculate moving mean. So, how will you calculate it? This part is fine, but when it comes to this, you are using this value, and moving variance, you are using this variance. Similar way, you will be doing for all the nodes. For all the nodes at hidden layer for the second mini batch. Similar way, you will now do it for the third one. If at all, if there are 15 samples, for every batch if you are passing 5 samples, 3 batches are required to complete the entire training data. Now, for the third mini batch, again you are passing the data, 5 samples you are passing, for every of the sample you are getting the values. So, at hidden layer Z1 you will have 5 values. For those 5 values you are calculating mean and standard deviation. For second node you have 5 values, those 5 values mean and standard deviation, and so on and so forth. Once you complete this, you have to again calculate moving mean and moving variance. Now, when you are calculating moving mean for mini batch 3, you will use the moving mean and moving variance of mini batch 2. What does it mean? You see this value, you are taking this. You see this value, you are taking this. Similar way, you see this value, we are taking this. This value, we are taking this, so on and so forth. I hope this part is clear. So, towards the end of one batch, how we are calculating mean and standard deviation, we are also calculating moving mean and moving variance. So, we have got 5 moving mean and 5 moving variance for each of the mini batch. Now, towards the end, we are going to freeze these values, freeze it meaning store it, so that we will be using it at a later stage. So, we are freezing these values. Now comes, you have completed the training. Now, the testing inference time, it is a testing phase. Now, during a testing, what exactly is happening? There is one sample that you have passed. There is a first sample that has passed. Now, when you pass the first sample, you are going to get Z1 here. You will be calculating Z1. So, a similar way. Now, when you get this Z, this Z has to be normalized. How do you normalize it? Normalization is mu standard deviation plus epsilon. This is the formula. Now, if a Z value has to be normalized, what is that mu and standard deviation we will be using? Because we have to normalize this Z1, because it is a batch normalization. During a testing phase, the sample will go through the entire model. When it reaches to batch normalization layer, the sample, the value has to be normalized. If the value has to be normalized during a testing, now we require this mean and then the standard deviation. From where do we take this? For Z1, when you are normalizing, this Z1 when you are normalizing, we will use the mean and we are using these 2 values here. Can you see? We are using this value and this value to normalize the sample during testing phase. Then you have the second node Z2. Now, Z2 has to be normalized. When Z2 has to be normalized, you will be taking these values. You will take this moving mean, this moving variance, and then you will substitute here. You will normalize Z2 with the help of moving mean and moving variance of mini batch, the last mini batch, not necessarily mini batch 3, the last mini batch of training. When it is Z3, for Z3 we will be using this sample, we will be using these values. Can you see, we are using these values. Similar way for Z4 we will be using this, and directly I am showing you for Z5. For Z5 we are using these values, right. Now, one question the student can get here is, ma'am, during a testing if I have some samples, because how do we write a code? 80% of the samples goes for training, 20% of the samples will come for testing. So, now in the testing I have 20% of the samples. So, can I pass the first sample and then get here the values? Can I pass the second sample and then get the values? So, during a testing time, can I, since I have many number of samples, can I use those samples mean and variance? The answer is no, or mean and standard deviation. How many ever number of samples that you pass during a testing, for every of those samples you are going to normalize by using the mean and the standard deviation of the previous that is the last mini batch. So, that you can see here from this particular slide. So, when you pass the first sample, you are going to normalize this Z1 by using the mean and moving standard deviation, moving variance of the previous the last mini batch during training. So, what is the advantage of moving a mean and moving a variance is, during inference time we want to normalize the values. Those values are normalized using this moving mean and moving variance. They are not the learnable parameters, they are just calculated and stored, so that you can use these values during the inference time. Even if you pass one sample or even if you pass n samples, for every of the sample you have to normalize the values, and you will normalize them using the moving mean and moving variance. That is the reason why we calculate moving mean and moving variance. So, this is what happens during a training part, and this is what happens during a testing. At inference also we have to normalize, right? We will normalize with the help of the moving mean and the moving variance. Then you will scale down the values, then the scaled value is then passed to an activation function. So, this is all about the batch normalization. So, we have two learnable parameters, that is beta and gamma, and there are two non-learnable parameters, that is moving mean and moving variance. So, this is all about the batch normalization working mechanism, and you can implement batch normalization even in CNN also, and it is an regularization technique that can be used in a neural network. You can implement it for multi-layer perception, or you can use it for CNN. In CNN, you can here in this particular code, the batch normalization is applied after activation function. After activation function, you are adding the batch normalization. Batch normalization is something that can be applied before activation, or it can be applied after activation. So, with this we have come to an end of this particular session. In this session you have explored how to prevent overfitting and the working mechanism of batch normalization. So, whatever I have explained to you, you can explain this graphically using this particular in this particular reference. This is just for a good visualization. So, in the next upcoming session, you will see a complete hands-on implementation of CNN, where you will be implementing CNN from the scratch, and then you will be taking an image data set. You will take some real time data, and then you will see how CNN has to be implemented, and you will also implement regularization techniques for CNN. Thank you.